Welcome from Data Science Made Simple. Until now, we have always used a straight line to describe the relationship between variables. But in reality, how many relationships are truly linear? So, which is this relationship? That's different? Yes, think about it. The outside the temperature rises by 1 degree. Does a building's energy consumption always increase by the same amount, for example? No. With mild temperatures around 18 and 20 degree, consumption is at the minimum because there's no need to heat or cool. But what happens if the temperature drops below 10 degrees? Consumption rises sharply due the heating. And if it goes about 25, consumption rises again due to air conditioning. So think about a scatter plot, okay? A U shape. If you look at these data points on a scatter plot, the shape that emerges is a clearing a U, a parabola, a straight line here would do a terrible job falling into what we call underfitting. The model is simply too simple to capture the complexity of the data. And to overcome this limit, we need a curve. And this is exactly the problem that nonlinear regression solves. Imagine having to describe a mountain road. A straight line would only tell you it climbs at the same slope, whereas a curve can faithfully describe climbs, flat stretches, and descents. Polynomial regression is the new term. For our U-shaped consumption data, the ideal choice is a degree 2 polynomial regression. But what does it mean, polynomial regression? The elegant trick of this method is that although the relationship between the variables becomes curved, the mathematical model remains linear in the parameters. How is this possible? By simply introducing new variables to our data set, for example, by squaring or cubing out temperature future. This allows us to use all the classic linear regression tools we already know, like Scikit-Learn library, by simply transforming the future first. So Scikit-Learn, the same library, okay? That we know. Danger of overfitting. However, there is a hidden danger behind polynomial models. Overfitting give an infinite set of points. There always exists a polynomial of sufficiently high degree that passes exactly through every single point. Sounds great, right? In practice, it's a disaster. Wow, it's no good. Imagine a student who, instead of understanding mathematics, memorizes word for word the solutions to 100 practice problems. If a slightly different problem appears on the exam, they're lost. The overfitted model does the same thing. It memorizes the noise and random variations of training data, performing terribly on new data. So this is a big issue. If you use a degree 15 polynomial for our building, we'd get a curve with wild oscillations at extremes, even predicting impossible negative consumption. The golden rule is this. The model should capture a trend, not memorize every single fluctuation. It's very important to distinguish between the two situations. Through nonlinear regression, to this front point, we have seen a method that reduces to linear regression. However, there are real-world relationships that cannot be modeled by polynomials, sorry, and require what is called true nonlinear regression. Here are some practical examples for distinguish. If your solar panel's efficiency, for example, degrades rapidly in early years and then slows down, you are dealing with an exponential decay curve. This is like this. Okay, if you measure a worker's productivity, you will discover that the first few hours are highly productive, but then diminishing return set in. The pattern again logarithmic model in this case. If you analyze phenomena with seasonal variation, like monthly energy consumption or over several years, you will need a periodic or sinusoidal model. For example, like this, sinusoidal. These models do not reduce to linear regression. To implement them in Python, we use iterative optimization techniques like SciPy optimized curve fit, which require explicitly defining the mathematical function that we are going to see in the slides after. So now we go to see the video, then my slides, then as you know, the podcast, and then we summarize together everything. Good view. Bye.
If you try to drive down a steep, twisting mountain road, locking your steering wheel perfectly straight guarantees a crash. Standard linear regression works exactly like that locked steering wheel. It is a highly efficient tool for mapping steady, continuous trends, but it is mathematically rigid. These models struggle because physical systems rarely follow a straight path indefinitely. Conditions fluctuate, limits are reached, and the data inevitably curves. Consider a physical dataset measuring a commercial building's energy consumption against the external outside temperature. At a mild 18 to 20 degrees Celsius, the HVAC system shuts down and energy consumption drops to its minimum. But as outside temperatures drop toward a freezing -10 degrees, the heaters draw massive power. Push the thermometer toward a sweltering 40 degrees, and the air conditioning grid works just as hard. When physical reality operates on a curve like this, applying a straight line produces more than just a minor error. It misrepresents the actual mechanics of the system. This scatter plot displays the building energy data. Temperature on the x-axis and energy on the y form a distinct U-shape. Forcing a standard linear regression model onto the structure generates a rigid line that awkwardly cuts through the empty middle of the chart. At these extremes, the error margins are massive. The model's predictions are completely disconnected from the actual energy spikes happening in the building. In machine learning, this specific failure state is defined as underfitting. An underfit model suffers from high bias. The algorithm assumes a simple, uniform relationship and ignores the actual complexity present in the data. To accurately predict this building's energy load, we have to find a mathematical mechanism that allows our rigid linear model to bend. There is a common misconception that modeling a curve requires abandoning linear algorithms entirely to use completely different, more complex tools. In reality, we solve this through a process called feature expansion. We engineer new data points by mathematically exponentiating the variables we already have. Look at the standard equation for polynomial regression. We start with our base variable, x, but add x squared, x cubed, and beyond. The original and its exponentiated versions are remapped into separate independent variables, x1, x2, x3. Once this substitution is complete, the resulting equation is identical to standard multiple linear regression. We haven't actually bent the line. We have mathematically warped the higher dimensional space it exists within, forcing a curve when mapped to 2 dimensions. This linear trick allows us to model highly complex reality while maintaining the exact computational efficiency of standard linear tools. Translating this theoretical math into production code requires a specific execution order in your pipeline. In Scikit-Learn, this is a two-step process. First, you run the raw data through PolynomialFeatures to generate the expanded array. Then you fit your standard linear regression model. When we apply a degree 2 polynomial to our building energy dataset, the trained model returns two distinct coefficients. The linear component is negative 12.4, which correctly pulls the predicted energy use down as the weather warms. But the squared component is positive 0.38, which acts as mathematical gravity, eventually pulling the curve back up as temperatures reach extreme heat. By adding a single squared feature, the standard linear algorithm perfectly discovers the building's 16-degree optimal comfort zone, resolving the underfitting problem. If expanding the features to x squared solved a simple curve, what happens if we add features up to x to the 15th power to capture every single nuance? Giving a model that much mathematical freedom introduces a new failure. The algorithm becomes hyper-reactive to individual data points. A degree 15 polynomial applied to our data violently spikes to hit every single dot perfectly, while wildly oscillating into impossible values in the empty space between them. Strictly on its training data, the model looks flawless, achieving a near-perfect R-squared score of 0.99. But the moment you ask this model to predict unseen test data, the output collapses. It predicts wildly inaccurate energy spikes, and the test score plummets to 0.23. This is a false positive. The algorithm hasn't learned the structural rules of the data. It has simply memorized meaningless, random noise. This failure is defined as overfitting. The model has excessively low bias, but its variance is so high that it cannot generalize to new information. Because excessive flexibility masks failure on training data, evaluating model complexity requires comparing performance across isolated data splits. This table compares R-squared scores across training and testing data. The degree 2 model sits in the sweet spot. Both scores are high and nearly identical, proving it learned a generalized rule. Conversely, degree 15 displays the absolute signature of overfitting, a massive delta between training and testing scores. The objective of machine learning evaluation is strict: capture the broad trend. Any capacity spent memorizing local fluctuations actively degrades the model's predictive power. Polynomial features solve the U-shape, but they contain a specific mathematical flaw. Regardless of the degree, a polynomial equation will eventually accelerate towards infinity. Real-world physical systems rarely accelerate forever. They encounter hard limits, physical ceilings, and structural floors. Look at a solar panel's degradation. This compound decay drops quickly at first, approaching a hard physical asymptote. Conversely, worker productivity rises sharply but flattens out, mapping diminishing returns. Because these phenomena do not accelerate endlessly, the linear trick cannot solve them. They demand explicit mathematical modeling via tools like SciPy's curve fit. This is why inductive bias matters. You must consciously choose a mathematical structure that mirrors the actual physical forces generating the phenomena. Professional nonlinear modeling begins with a strict visual assessment to formulate a structural hypothesis. U-shapes require polynomials, accelerating curves require exponentials, and flattening curves require logarithmic functions. Once the model is trained, monitoring the gap between train and test scores is your primary defense against the overfitting trap. Finally, use residual analysis. If clear patterns remain in your error margins, your mathematical structure is still incomplete. Ultimately, regression modeling isn't about perfectly connecting dots on a chart. It's about identifying the specific mathematical relationship governing the data, allowing for reliable predictions in a world that rarely moves in a straight line.
Welcome to this introductory reaction on polynomial and nonlinear regression. Today we'll learn how to overcome the limitation of simple straight lines by analyzing the real-world datasets, such as energy consumption, solar panel performance, and work productivity. When a straight line is not linear, enough. If we analyze buildings, for example, energy consumption against the outside temperature, we notice a U-shaped pattern. At 18 and 20 degrees, consumption is at its minimum, but it rises sharply both in the cold for heating and in the heat for air conditioning. A straight line here cannot capture the structure of the data, a problem we call underfitting. It's like trying to describe a mountain road with a straight line. It doesn't work. We need a curve that captures climbs, flat stretches, and descents. This is why we resort to nonlinear regression, which can use polynomial models, exponential models for growth, logarithmic models for diminishing returns, or sinusoidal models for seasonal patterns. Polynomial regression, the linear trick. Let's focus on polynomial regression, which uses a very elegant mathematical trick. By adding powers of our original variable, like x squared or cubed, we create new features. By doing so, the mathematical model reduces to a classical multiple linear regression. In Python, we just need to use PolynomialFeatures from the Scikit-Learn library to transform the data and then apply the usual linear regression. On our consumption dataset, a degree 2 polynomial creates a perfect parabola, identifying the building's optimal comfort temperature at around 16 degrees. Overfitting versus underfitting, choosing the right degree, but be careful not to overdo the polynomial degrees. At this table, show us let's change my face here. Degree 1 is too simple and underfitting. With underfitting, there's not a thing. Degree 2 is our sweet spot, perfect balance. But if we go up to degree 15, we fall into the disaster of overfitting. The model gets a near perfect score on the training data, but completely collapses on the test data because it has memorized the random noise instead of learning the pattern. Remember the golden rule: the model must capture the general trend, not chase every single fluctuation. If there is a large gap between the training and test scores, you are overfitting. The slide 5, through nonlinear regression, exponential log periodic. However, there are cases where polynomials are not suitable and you need true nonlinear regressions. At first example is solar panel efficiency. It decays rapidly in early years and then slows down. This requires an exponential curve with a decay and a long-term asymptote. A second example is worker productivity based on consecutive hours. The first hours yield a lot, but then diminishing returns set in, typical of the logarithmic model. Unlike polynomials, these models do not reduce to linear forms. They are required to use the use of specific techniques in Python, such as the SciPy optimized curve fit function, explicitly define the mathematical equation. How to choose the right regression model. So how do you choose the right model? Follow these steps. Visual analysis, scatter plot. First, visual analysis, look at the scatter plot. If it's U-shaped, use a degree 2 polynomial. If it grows even faster, use an exponential. If it grows but slows down, use a logarithmic. if it is oscillates, try a sinusoidal model. Second, test and compare. Always evaluate the error gap between training and test data to avoid overfitting. As you can see, residual analysis. Do a residual analysis. Plot the residual against predicted values to ensure no patterns were missed by the model. Advanced machine learning. If you none of this work, you can move on the advanced machine learning algorithms like random forests or neural networks. Okay, and in the code below, you can see how Scikit-Learn pipelines make applying and evaluating these models. Extremely clean and effective. Now we summarize the key concept of the day. We step outside the boundaries of straight lines by using nonlinear equations when the data requires it. Remember that polynomial regression reduces to multiple linear regression by adding new features, but it carries the severe risk of overfitting if the degree is too high. Exponential and logarithmic models must be handled differently using Cypher fit with an explicit mathematical function. And your compass for navigating will always be the initial visual analysis. Thank you for your attention, and now we are going to see the video cinematic. Thank you so much.
Welcome everyone to Data Science Made Simple by Gabriele Fusi. Today we are exploring nonlinear and polynomial regression, understanding why straight lines often fail to capture real-world behavior and how machine learning models can learn curves, nonlinear patterns, and complex relationships. This is not just theory. This is a complete visual and practical walkthrough where we analyze every slide, every chart, and every code block step by step.
And this mission is incredibly crucial. You know, real-world data is rarely a perfectly straight line. I mean, if you force a simple linear model onto complex phenomena, you are going to get disastrous predictions. So today, we fix that.
Right. We're going to give you the mathematical tools and the actual code to capture the true hidden shapes of reality.
Exactly.
But before we pull up the first slide, I want you to think about driving up a mountain. If you tried to use a perfectly straight line to describe a mountain road, you'd basically be implying that the road just climbs upward forever at the exact same unchanging slope.
Right, which never happens.
Yeah. I mean, if you've ever driven through the mountains, you know real roads have steep climbs, then they flatten out, and then they have sharp descents. If your navigation system assumed a straight line, you'd drive right off a cliff.
That is honestly a perfect analogy for what we are doing today. A straight line is mathematically rigid. It cannot adapt to the climbs, the flats, and the descents of your data.
So we are essentially embarking on a visual coding bootcamp together to learn how to adapt. Let's dive right in. I am pulling up slide 1, Mastering Nonlinear and Polynomial Regression.
Let's start with the core problem here. How many relationships in life actually go up or down at a constant straight rate?
Very few. Right?
Exactly. Very few. When you look at physics, biology, or, human behavior, systems are curved. Nonlinear regression is the statistical method we use to find the right curve for this data.
So instead of just drawing a simple straight line, we're using like polynomial, exponential, or logarithmic equations to map out those bends and turns. To see exactly why a straight line fails so badly, let's map out a real-world scenario. Moving to slide 2. When a straight line underfits reality.
Okay, so picture this.
Right. If you were to graph this data set out, mapping 365 days of a building's energy consumption on the vertical axis against the outside temperature on the horizontal axis, you'd see temperatures ranging from a freezing negative 10 degrees Celsius all the way up to, like, a sweltering positive 40 degrees Celsius.
Now, think about the shape those data points would form. At around 18 to 20 degrees Celsius, the energy consumption is at its absolute lowest point on the graph.
Which makes perfect sense because the weather outside is mild, you don't need the heating, and you certainly don't need the air conditioning.
Exactly. But if you follow the graph left, dropping below 10 degrees, the energy consumption spikes upward because the heating system kicks into high gear.
Oh, right.
And then if you follow the graph to the right, rising above 25 degrees, the consumption spikes upward again because the AC is running at full blast. So the data points form a perfect U-shape, a classic parabola.
And this is exactly where we encounter the concept of underfitting, isn't it?
It is. If you try to draw a straight line through this U-shape, it is going to be a terrible model. I mean, it might predict high consumption when it should actually be low, and low consumption when it should be high.
Yeah, a straight line underfits reality because it's just entirely too simple for the complexity of the data structure. It cannot bend.
Right. We need a curve. Specifically, we need polynomial regression.
Okay, but how do we actually draw that curve using machine learning? We are going to solve that right now on slide 3. The linear trick. Redefining the features. This is where the math gets incredibly elegant.
It really is a brilliant mathematical trick. The formula for a second-degree polynomial, a parabola, is mathematically written as y hat equals theta 0 plus theta 1 times x plus theta 2 times x squared.
Right, and because of that x squared term, it looks like a purely nonlinear equation.
It does, but the trick is that the model actually remains linear in its parameters, which are the thetas.
Wait, let me stop you there and make sure I'm clarifying this trick for everyone. So you're saying if we just mathematically pretend that x squared is a brand new independent variable, let's call it x2, our complex curved equation just transforms back into standard multiple linear regression.
Precisely. By creating new expanded features out of thin air, so your first feature is just x, your second feature is x squared, your third is x cubed, we are simply adding new columns to our data set.
Wow.
Yeah. Once we do that, we can use the exact same standard linear regression tools we already know to solve a completely curved nonlinear problem.
That is honestly mind-blowing. We don't even need a new machine learning algorithm. We just need to change the shape of the data we feed into the algorithm.
Exactly.
Let's see how this looks in practice. We're moving to slide 4, implementing the polynomial transformation. Let's look under the hood at the code. This is code block 1.
Let's walk through the commands line by line.
Okay, code block 1. Line 1. We set a variable called equal to polynomial features, passing in the parameter degree set to 2, and include Labius set to false.
So, line 1 creates the polynomial features transformer. We are setting the degree parameter 2, which tells Scikit-Learn we want to create quadratic features, specifically those x squared terms, to handle our U shape.
And we also set include your bias to false, right?
Right, because our linear regression model will automatically calculate its own intercept later on. A really common beginner mistake is leaving this as true, which creates redundant data and just messes up the model's math.
Good to know. Okay, line 2. We set xpoly equal to poly.fitTransform, passing in our original data, x.
Line 2 transforms the original feature space. This is where the actual mathematical expansion takes place. The input is our original feature space, just the outside temperature. The output is a newly expanded feature space containing both the temperature and the temperature squared.
So our dataset shape goes from 365 rows in one column to 365 rows in 2 columns.
You got it.
Finally, line 3. We set reg equal to linear regression dot fit, passing in our newly created xpoly and our target variable, y.
And line 3 trains the linear regression model on the transformed data. Notice the crucial detail here. We are feeding it the expanded data, xpoly, not the original linear data.
Let's look at the output that this model actually gives us. The model prints out energy equals 285.1 minus 12.4 times temp plus 0.38 times temp squared.
Let's unpack the mathematical intuition behind those coefficients. The negative 12.4 is the linear drop. It represents how energy consumption initially goes down as the freezing winter temperatures start to warm up.
Right. But then we have the positive 0.38.
Yes, that is the positive quadratic component. As the temperature keeps increasing into the summer, that squared term grows exponentially faster, forcing the line to stop dropping and actually curve back upward, creating that beautiful U shape.
And if you use calculus to find the absolute minimum point of this mathematical curve, it hits exactly at 16 degrees Celsius. That is the building's optimal comfort zone where energy use is lowest. It's amazing how the math perfectly reflects reality.
It really is.
But wait, if expanding the features gives us a curve, why stop at degree 2? Why not just use like degree 10 or degree 100 to make the model perfectly accurate? This brings us to a major warning on slide 5, the overfitting trap?
It's a great question, and it leads into, well, perhaps the most dangerous trap in machine learning. If you use a polynomial degree that is too high, say degree 15, the curve will become so incredibly flexible that it will snake around and pass exactly through every single historical data point in your data set.
But wouldn't passing through every single point mean the model is perfectly accurate?
It is a complete illusion of accuracy. This is what we call overfitting. Think of it like this. The model is memorizing the random background noise, the anomalies, and the minor fluctuations in your data, rather than actually learning the broad underlying trend.
Oh, this reminds me of a great analogy, the memorizing student. Imagine a student who, instead of actually learning the underlying mathematical formulas, just memorizes 100 practice problems word for word.
Right. They even memorize the font the test is printed in.
Exactly. They get 100% on the practice test. But the moment they sit down for the final exam, and a problem is phrased just slightly differently, they completely fail because they never learn the actual concepts.
That is exactly what an overfitted model does. A classic beginner mistake is assuming a higher degree means a better or more powerful model. But an overfitted model will predict wildly impossible values the moment it encounters new, unseen data.
Let's visualize this exact failure. I am moving to slide 6, the bias-variance dial, choosing the degree. The chart here shows 4 overlapping curves, comparing the R-squared scores for both the training data, which the model has seen, and the unseen test data.
This chart illustrates the bias-variance trade-off perfectly. It's the central tension of all machine learning, really.
Let's run through these options. First, degree 1, which is just our linear straight line. It has awful scores, an R-squared on the train set of 0.12 and on the test set, 0.10.
That is classic underfitting. We call this high bias. The model is too stubborn and too rigid to see the U-shaped pattern right in front of it.
Then we skip to the other extreme, degree 15. The training score is an amazing 0.99, but the test score is a disastrous 0.23.
Yeah, that's rough.
In fact, the visual curve for degree 15 swings so wildly at the edges of the chart that it's predicting negative energy consumption, which is physically impossible.
Severe overfitting, high variance, it's way too reactive. It memorized the noise, the training data, and entirely collapsed when exposed to the reality of the test data.
So we look at degree 2, our simple parabola. The R-squared for the train set is 0.89, and for the test set, it is 0.87.
That is the sweet spot. The golden rule here is to capture the trend, not the fluctuations. A very small gap between training and test scores means the model actually learned the true shape of reality, rather than just memorizing the past.
Okay, so we've solved the U-shape with a clever polynomial trick. We forced a linear model to bend. But what if our data doesn't fold neatly into a parabola? What if it decays infinitely, like battery life?
That requires a completely different approach.
Which brings us to slide 7, beyond the hack. True nonlinear modeling.
This is a vital distinction in data science. There are many real-world relationships that polynomials simply cannot describe accurately. Things like exponential growth or decay, logarithmic curves that show diminishing returns, or periodic data that moves in a sinusoidal seasonal pattern.
Right.
Because the parameters, the thetas, enter into these equations non-linearly, like being stuck up in an exponent or trapped inside a logarithm, you absolutely cannot use the standard Scikit-Learn linear regression trick.
Okay, so if standard linear regression is completely off the table, what do we do instead?
You must use iterative optimization techniques. We are going to use a tool from SciPy called scipy.optimize.curvefit. It basically uses calculus to incrementally adjust the parameters over and over until the curve fits the data.
I want to make sure I grasp the difference here. So standard linear regression is like solving a puzzle where all the pieces have straight edges. There's one exact mathematically solvable answer. But this curve fit method, is it more like tuning a guitar by ear? You tweak the parameters a little bit, listen to how close you are, and keep incrementally adjusting until the math sounds perfect.
That is a phenomenal way to explain it, yes. Linear regression uses analytical math to jump straight to the answer. Curve fit uses iterative calculus to basically feel its way to the answer step by step.
Let's see, this is guitar tuning in action on slide 8. Engineering the equation. We are looking at 2 new data sets here. The first data set tracks solar panel efficiency over years of use.
And the underlying formula is exponential decay. Y hat equals theta 0 times e to the power of theta 1 times x plus theta 2.
We have code block 2 here to implement this. Let's look at the Python implementation line by line.
Let's break down the functions.
Code block 2. Line 1. We write defist exponential model. X, theta 1, theta 2.
Line 1 defines a custom Python function. Because we aren't using a pre-built linear model, We have to tell the computer exactly what the mathematical shape looks like. The inputs are x, which is our years of use, and the 3 parameters we want the model to iteratively discover.
Okay, line 2. Return the e times np.exp, a 1x, plus the add 2.
Line 2 is the actual mathematical formula returned by the function. We used NumPy's exponential function to calculate the decay curve over time.
Got it. Line 3. We set popped, peak off equal to curve fit, passing in our exponential model function, our x years data, our efficiency data, and a parameter called p0, which is set to a list containing 50, negative, 0.1, and 50.
Line 3 runs the iterative optimization.
Wait, let me challenge this. Why do we have to provide this p0 list of numbers? We didn't have to provide guesses for linear regression.
Because of exactly what we discussed with the guitar tuning analogy. Because this is an iterative process, P0 provides the model with our initial starting guesses for the thetas. It tells the algorithm where to start turning the pegs.
Ah, I see.
Yeah, without a decent starting guess, the calculus might wander off in the wrong direction entirely. When the tuning finishes, it outputs popped, which contains the final optimized parameters.
And looking at the results, the model finds that theta 1 is a negative number, specifically negative 0.089.
That negative theta 1 is what mathematically drives the rapid initial decay of the solar panel. It means the panel loses efficiency fastest in its early years.
And theta 2 comes out to 51.8, which acts as the long-term asymptote.
Exactly. That means no matter how many decades pass, the efficiency will flatten out and never physically drop below roughly 51.8%. If you plug in 0 for years, the total is exactly 100%. The math is flawless.
That is fascinating. Now, the second data set on this slide is a logarithmic model, looking at worker productivity versus work hours. The formula is y hat equals theta 0 plus theta 1 times the logarithm of x.
This represents the classic idea of diminishing returns.
Right. The real-world truth is that your first few hours of work yield huge results. But as you get to hour 8, 9, or 10, your brain is tired, you're experiencing burnout.
Oh, absolutely.
The later hours have steeply diminishing returns. The math shows that every time you double your hours, you only yield an additional 19.6 units of productivity. It slows down logarithmically.
Exactly. You are engineering the mathematical equation to match the underlying psychology of the problem.
So, with all these incredible tools at our disposal, polynomials, exponentials, logarithms, how do you actually choose which one to use in the wild? Let's pull up slide 9, the model selection operating system.
You need a structured workflow and operating system for your analysis so you aren't just guessing. It essentially boils down to 4 steps. Step 1 is visual inspection. Always plot your data first. Look at the scatter plot. Is it a U-shape? Try polynomial. Does it grow rapidly and then slow down flat? Try logarithmic.
Step 2 is test and compare. You take your candidate models and you compare the R-squared scores of the training set against the unseen test set to catch overfitting, just like we did with the bias-variance dial.
Right. Step 3 is residual analysis. You calculate your errors, the residuals, which are just your predictions minus the actual reality. If you plot those errors on a graph and they still have a visible curve or a shape to them, it means your model is incomplete.
So the errors should just look like a completely random static.
Exactly. If they don't, you missed something structural in the data.
And finally, step 4 is advanced ML fallbacks. If none of these mathematical equations fit the data, you pivot to powerful algorithms like random forest, XGBoost, or neural networks, which build their own non-parametric curves.
Exactly. You scale up the complexity only when the simple math fails.
Okay, we are entering the home stretch. We've chosen our model, but we need to build it properly for production. Let's look at slide 10, the master pipeline. This brings us to code block 3.
This is how the professionals ensure their code doesn't break in the real world.
Okay, code block 3, line 1. We write pipeline lines.
Line 1 initializes a Scikit-Learn pipeline object. This allows us to chain multiple data processing steps together into a single unified workflow.
Got it. Line 2, scalar, standard scalar.
Line 2 is critical. Standard scalar normalizes our numerical values. When you start squaring and cubing numbers, they get massive.
Yeah.
Normalizing ensures those very large numbers don't mathematically overwhelm the very small numbers during the calculation.
Makes sense. Line 3, polynomial features degree 2 include POMI is false.
Line 3 is the transformer we discussed earlier, expanding our features to include those quadratic squared terms.
Line 4, reg linear regression.
Line 4 is the final step, training the actual linear model on the scaled and transformed data.
And line 5 just closes the pipeline with reg.
Right. By closing the pipeline, you have created a single object that you can call fit or predict on. Beginners should always use pipelines because it guarantees that pre-processing and modeling are locked together.
And that ensures perfect reproducibility and completely prevents data leakage, right?
Exactly. Data leakage is when information from your test set accidentally bleeds into your training set, giving the model the answers in advance and ruining your validation. Pipelines stop that dead.
And what's the output of this production pipeline on our building energy data? We get an R squared of 0.87 and a root mean squared error, an RMSE of 24.35 kilowatt hours.
Which is fantastic.
Yeah, considering the building's energy ranges from 180 to 620, being off by only 24 is incredibly precise. This is a highly accurate deployable model.
It is entirely ready for the real world.
Let's bring it all together on our final slide, slide 11, system cheat sheet. Let's do a rapid summary of our code along.
Right, so we learned that underfitting happens when a model is too simple, like forcing a straight line onto a U-shaped curve.
We learned the polynomial trick, creating new expanded features like x squared, so we can cleverly use standard linear regression to solve curved problems.
We saw the immense danger of overfitting, where a model memorizes the noise instead of learning the pattern, acting like a student who memorized the test instead of the concepts.
We explored true nonlinear models like exponentials and logarithms, which require iterative optimization like tuning a guitar using curve fit because they cannot be reduced to linear tricks.
And we established a four-step workflow strategy. Visualize the data, compare test scores, analyze the residuals, and fall back to advanced ML to ensure you always find the exact right curve for your problem.
What an incredible session. Before we go, I want to leave you with a thought to mull over. Think about the assumptions you make in your own life or in your business. How often are you projecting a straight line into the future?
That's a great question.
How often do you assume that your costs, your personal growth, or even your daily burnout will just scale linearly forever? Think about it. The reality is almost certainly a hidden U-shape or an exponential curve just waiting to reveal itself if you actually stop and look at the data.
Nonlinear regression teaches us that reality is rarely a straight line. The power of machine learning comes from discovering the hidden shape behind the data. This was Data Science Made Simple by Gabriele Fusi.
It was an amazing video and the podcast that explain very well these concepts that is not too common talk about it because generally we are faced with linear regression, with neural network, and this concept is not usual to face. And now I would like to explain all the concept with an infographic that summarize everything. Very simple, nice to see, and now we go again into all the concept. So we see this infographic, our visual guide on nonlinear regression. We are going to explore how to model data when a simple straight line just isn't enough. The section now when lines fail. Let's start by looking at the first panel, showing a scatter plot of a building's energy consumption against the outside temperature. Notice this distinct U-shape. At the mild temperatures, energy use is low, but it spikes when it's very cold due to heating or very hot due to air conditioning. If we try to draw a straight line through this, we get what is called overfitting. The linear model is simply too basic to capture the curved structure of the real-world data. To accurately describe this mountain road, we need a curve. The polynomial trick, moving down to the next section, we see our first solution, polynomial regression. Here we use a very elegant mathematical trick. By taking our original variable and adding its powers, like squared or x cubed, we create new features. Because of this future expansion, the math actually reduced to a standard multiple linear regression. As you can see in the Python snippet, we just use polynomial feature from the Scikit-Learn library to transform the data and then apply the classic linear regression algorithm. For our U-shaped energy data, a degree to polynomial creates the perfect parabola. The section 3 overfitting trap, but look at the warning section right next to it, the danger of the overfitting. The infographic shows different polynomial degrees. Degrees 1 underfits the data. Degrees 2 is our sweet spot, perfectly capturing the U-shape. But if we crank it up to degree 15, the curve goes completely crazy. It hits every single training point perfectly, but it memorizes the random noise instead of learning the true pattern, even predicting impossible negative consumption values at the extremes. Remember the golden rule, highlighted here. The goal is to capture the general trend, not to memorize every fluctuation. If your training score is much higher than your test score, you are overfitting. In the section True Nonlinear Models, we look at the bottom left panel showing true nonlinear regression. Not every problem can be solved with a polynomial trick. For example, if you are tracking the degrading efficiency of solar panels, over time we need an exponential decay model that eventually flattens out. Or if we track worker productivity over consecutive hours, we see a logarithmic curve representing diminishing returns. Unlike polynomials, these models do not reduce to linear equations. To use them, we rely on optimization tools like CPy optimized curve fit, where we must explicitly define the mathematical formula. How to choose the decision workflow. Finally, let's review the decision flow chart at the bottom. How do you choose the right model? First, do a visual analysis. If it's a parabola, use a polynomial of degrees 2. If it grows even faster, use an exponential model. If it grows but slow down, use a logarithm. If it shows regular seasonal patterns, use a periodic or a sinusoidal model. Second, test and compare. Always compare your training and test scores to avoid the overfitting trap. Third, check your residuals to see if any hidden patterns were missed by the model. And if all else fail, the flowchart points us the advanced machine learning algorithms like random forests, XGBoost, or neural networks. Thank you for exploring this guide, and happy modeling. We will see in the next video. Thank you for listening me, and see you soon for the next video. Bye.